Okay, here I've got a video about how to solve compound inequalities. And first I want to kind of look at the difference between what we call an OR inequality and AND inequality. For a number to be a solution to an OR inequality, it just has to satisfy one or the other. Meaning if I said, are you a boy or a girl, that would be everybody. No one satisfies both boy and girl, but you can satisfy one or the other, so you would be a solution to that. Now here, if I said x is less than 2 or x is greater than 5, if I pictured that on a number line, if here's 2 and here's 5, the numbers less than 2 are over here, and the numbers greater than 5 are over here. And so we can see that there's no numbers that are both less than 2 and greater than 5, but these numbers that I have shaded in are the solutions to this inequality, because they're solutions if they satisfy one inequality or the other. Once again, like for example, 0 is a solution to this inequality because it's less than 2. It's not greater than 5, but it doesn't have to satisfy both. So that's an OR inequality. Honestly, that's not the kind we're going to focus on with this video, because you don't really see those as much later on in math. Here we've got an AND inequality. Now here, if I said x is less than 8 and x is greater than 6, I can plot that on a number line. Here's 6, here's 8. So if I said here's the numbers greater than 6, and I shaded them that way, and if I said here's the numbers less than 8, and I shaded them that way, I can see the only numbers that satisfy both are solutions to this inequality. So where my shaded regions overlap, that's my solution right here. So it doesn't include 8 and it doesn't include 6, but it includes all these values in between. Now, the way we can rewrite this compound inequality is I'm going to rewrite it like this. I'm going to come below it right here. I'm going to rewrite it with this on this side. So I just wrote this inequality here and this inequality here. Well, I know that if x is greater than 6, that's the same thing as 6 is less than x. So I have 6 is less than x and x is less than 8. Well, since I've got an x there in both of them, I can just write that all together, because I know that 6 is less than x, and I know that x is less than 8. So that's how you can rewrite the compound inequality. I always like to put my lower number here on the left and my greater value there on the right. So that's kind of some of the theory. Let's look at it in action. Here, we're going to write a compound inequality, then we're going to graph it. So this says all real numbers that are less than 6 and greater than 2. So if I have a number that's less than 6, that would be x is less than 6. And x is greater than 2. Well, I'm going to do those same steps I just showed you on that previous example. I'm going to rewrite it with this over here, because I know that 2 is going to be my lower number, and I like to have that on the left. And then I can rewrite it. I want my x's in the middle, so I can just write those x's together. So I'm going to reverse this first inequality. If x is greater than 2, that's the same thing as saying 2 is less than x. And now that I have those x's on the middle, I can just combine them and say 2 is less than x, which is my first inequality, and then I know that x is also less than 6. So that's how I would write this sentence as a compound inequality. If I were to graph it, we know from that previous example that if here's 2 and here's 6, I'm not including those values because we're less than 6 and greater than 2. So we don't include those boundary numbers, but we're going to include everything in between them, because those are the possible values of x that are described here. Let's look at our second example. All real numbers that are less than or equal to 8, less than or equal to 8, that's our symbol for less than or equal to. Now we're including the 8, and x is greater than -1. So I'm rewriting it. I want my lower or my smaller value of -1 on the left. And then I'm going to flip this inequality just like we did in the previous example. And now my last step is just to write these as a single inequality. -1 is less than x, and we see right here that x is less than or equal to 8. So if I'm putting these on a number line, here's -1, here's 8. I'm not including -1 because x is greater than -1. That means -1 is not a solution. But if you look over here, I say x is less than or equal to 8. The way I show that on the number line is I shade in this circle. And then I know that it's all values in between those. So that's how I write as a compound inequality, and that's how I represent those values on a number line. Let's go to some little more difficult examples. So here I see that I'm trying to solve these and then graph. Now, I'm going to solve this to kind of show you the theory behind what I'm doing here. Notice that 6 is less than x plus 5, and that same value of x plus 5 is less than or equal to 11. Well, we know how to solve these two-step inequalities. I'm just trying to solve for x, so I'm going to subtract 5 from each side and get that 1 is less than x, and I'm going to subtract 5 from each side here and get that x is less than 6. Now, write that as a compound inequality, and then I could always represent it on a number line. So that would be my solution on the number line. Now here's what I want to see. Since these values right here are the same, I can write those together, just like we did in these previous examples. Once these values right here are the same, I can write it as a single inequality by writing them together. That's what I've done in this second example. Instead of saying 6 is less than x plus 5 and x plus 5 is less than 11, that's an or equal to, isn't it? I missed my or equal to sign. That's why it's always good to check your work. But if I have that 6 is less than x plus 5 and x plus 5 is less than or equal to 11, I can write it like this. Now let's look at our first step to solving it. The first thing we did is we subtracted that 5 from each side because we're trying to get x by itself. That means I'd subtract 5 to get x by itself, but I'd also subtract it there, and I'd also subtract it there. So now it's kind of like there's 3 parts that I got to subtract 5 from. Then I end up with my 1 is less than x, which is less than or equal to 6. Once again, number line. I'm going to make sure I get my or equals to on that 6 this time. But that's how I represent it on a number line. Okay? Now that we've talked about the theory, here is an example that adds one small step. I'm starting here. So I'm going to begin by subtracting 3 because we're trying to get x by itself. Anything I do there, I'm also going to do there, and I'm also going to do there. So I end up with 1 is less than or equal to negative 2x, which is less than or equal to 6. Now I've got to get x by itself, so I'm dividing everywhere by negative 2. Now if you remember from solving two-step inequalities or from solving multi-step inequalities, let me see, this is going to be an x and that's going to be a negative 3. Whenever I divide by a negative, I have to flip my inequality symbol. That same thing is still going to apply here. So that less than or equal to becomes a greater than or equal to. And that less than or equal to 6, or I guess a negative 3, becomes a greater than or equal to. So I flip my inequality symbols now. Well, I always want, just like in our previous examples, I like that smaller value written on the far left. We know that negative 3 is further to the left on a number line than negative 1/2. So I'm going to flip this entire inequality. But if I do that, I got to also flip my symbols back. So what I've done is I reversed my entire inequality so that I've got my smallest value on the left, and then I can represent it on my number line. These times are both shaded because they're both or equal to, and the solution is all the values in between them because x is in between those two values.